Good afternoon. Welcome to the APL Colloquium. This is our first Zoom webinar colloquium. Hopefully there are a lot more to follow. Zoom webinar is an experiment for us, and we're still learning about the tool and how to run it. Please excuse any mistakes we make. And if you have comments or suggestions, please send them to colloquium@jhuapl.edu. Again, please be gentle. The audience is muted, so please enter your questions in the Q&A section, and we'll try to address as many as we can within the time limits. Moving ahead, our guest today, Leonard Rodberg, is a physicist by training and a professor emeritus of urban studies at Queens College, City University of New York, where he taught for 35 years before retiring in 2016. Professor Rodberg has a background in nuclear physics, public policy, and healthcare policy, and has taught computer-based analysis addressing problems in those areas and climate change as well. Early in his career, he was chief of the Science Policy Office in the U.S. Arms Control and Disarmament Agency within the State Department. And with a big round of silent applause, Len, it's over to you.
Thank you very much. I'm pleased to be here. The last time I was at the lab actually, since my son works there, I was at a party there 2 years ago, but the last time I spoke was 1965, and I was speaking on nuclear arms control. And it feels like deja vu because I'm going to be talking about nuclear power again today. A little more about myself. As Dan said, I was trained as a nuclear physicist. In the 1960s, I did a lot of work on energy conservation and solar energy, and I wrote a report for the Congress on the millions of jobs that solar energy and wind would produce if we took them really seriously. I then moved to New York and taught urban studies and climate change. In the course of that, I taught my students what is still today the conventional wisdom, which is that a vast expansion of renewable energy, solar and wind particularly, is essential to meet the challenge of climate change. And that nuclear energy is too risky and too expensive to be a part of, even though it's carbon free, it is not appropriate for what we really need. After I retired 4 years ago, I started to look much more seriously into this issue, and I discovered I was wrong on both counts. And what I want to do today is explain to you why I was wrong and what I believe the facts are. So first of all, we've got to take climate change seriously. The temperature is obviously rising, and we're seeing its consequences in many different areas around the world. We have to act in response to it, but we still haven't decided how in an effective way. Here's the way climate scientists look at why the climate is changing. Basically, there's an energy imbalance, which is causing the temperature of the atmosphere and the Earth overall to rise. Basically, we're absorbing more heat from the sun than we're emitting. The principal reasons are the addition of extra carbon dioxide and methane, CO2 and CH4, into the atmosphere. There are counter effects like clouds, and actually the warming is melting the ice caps, but it leaves the ocean to absorb more heat. The net radiative forcing, as the climate folks call it, is positive and dangerous. And one of the major lessons is we have to reduce the addition of long-lived greenhouse gases to the atmosphere. We're not doing very well at it right now. This shows the principal sources of energy worldwide. Those that contain carbon dioxide, those that emit either carbon dioxide or carbon in the form of methane, are overwhelmingly the major sources of energy today, and they're continuing to grow. The zero carbon sources, which are hydroelectric power, some forms of bioenergy, of burning of biomass, nuclear power, wind, and solar are growing, but still very, very small relative to the carbon emitting sources. So here's how we produce electricity here in the United States. I actually love this diagram. It shows so much once you understand it, and it becomes very clear. I always referred to it as a spaghetti chart until I discovered that it's technically called a Sankey diagram, after a British ship captain who used it, invented it to explain how steam engines worked. Basically, it's a flow diagram, and the thickness of the lines are proportional to the amount of flow in each source. The sources of energy are on the left. I can now use my mouse pointer over here on the left. A portion of those sources are used to generate electricity, and then we move over here to the sectors of our economy that use the energy. And finally, we have the useful energy services and the waste energy, because we never can actually use energy with 100% efficiency, and particularly when we generate electricity by boiling water, we're limited by the laws of entropy to wasting 2/3 of it. This chart is also useful because it's in quads or quadrillion British thermal units, and it happens that total energy consumption in the US is just about 100 quads. It actually has been that for several decades. We've even as our economy grows, we've gotten more efficient at using energy, and for a whole variety of reasons. But the thing I want to point out is solar is, and so we can treat, because it's 101 quads, we can basically treat the number of quads as a percentage of total usage. And you can see that solar, which is used to generate electricity, is still less than 1% of our total energy use, even though it and wind energy have been the beneficiaries since the 70s of substantial subsidies from the federal government and from state and local governments as well. Wind energy, you can see, is about 2.5% of the total energy use. Nuclear is 8%, and I'm going to, of course, come back and talk about that some more. The fossil fuels are here: natural gas, coal, and petroleum. You can see that coal is mainly used for electric generation. You can also see the electric generation is about 38% of our total energy use. It's, of course, not a final, it's not final energy. It's then used in one of the practical sectors, including here in New York City. A little bit of it drives our subway system. Here's Maryland's use of energy. It's somewhat similar. Nuclear energy provides 38% of its electricity. This is the sources of electricity in Maryland. We still burn a lot of coal here. The renewables and hydro are very small. There's Susquehanna River, the Conowingo Dam up here, but the renewables are still very, very small in total. And I thought, remind you, here's where the nuclear generated electricity comes from the Calvert Cliffs plant on the Chesapeake Bay. I call your attention especially to the cost, because I'm going to come back to cost in a little while. It cost $2.2 billion in 2007, or basically current dollars, and generates 1,700 megawatts, a little more than $1 billion per gigawatt. A gigawatt's 1,000 megawatts. Today, a nuclear plant built in the U.S. costs somewhere between $8 and $10 billion per gigawatt, rather than one. I'll talk more about that in a little while. Okay, so the major issue we face with the climate is, how do we get rid of fossil fuels? How do we get rid of the burning that generates carbon dioxide and methane? By the way, some of the methane comes from leakage in the pipelines, leakage from the wells from which natural gas is extracted, not from the burning of the methane, but from the leakage of the methane. So, as I said, the most popular belief is that they should be replaced with renewable energy, with wind farms, wind turbines, solar panels, photovoltaic panels, and hydropower. But there are other ways of generating energy that don't produce carbon dioxide, methane. One is with nuclear power. Another is by using storage. This is a Tesla storage system in Australia. Storage isn't a source of energy, of course, but it's a way of saving some of the intermittent energy that solar and wind will produce, and then using it when you need it. This is a picture of a carbon capture and sequestration demonstration facility. Basically, you burn fossil fuels, but then capture the carbon dioxide before it can get out into the atmosphere. It adds to the cost, and it's not hasn't been actualized to any place in the world at a commercial level. So here's the most popular way that people envision addressing the climate change, with the problem of climate change, which is, this is from Mark Jacobson, who's a professor of civil engineering at Stanford and kind of the guru of the 100% wind, water, and solar model for how we should address climate change. This is a year ago, some more than 600 organizations, nonprofit organizations, citizen groups around the country petitioned the Congress to pass legislation that would move us to 100% renewable energy, excluding all forms of combustion. That's a quote from their petition, excluding all combustion-based power generation, just using wind, water, and solar energy. And the other principal Democratic candidate for president this year, Bernie Sanders, also advocated 100% renewable and stopping the building of all nuclear power plants and a moratorium on any extensions of their life. A number around the country, including one here in New York City, have been closed over the last few years, even though they were working quite normally. So let me look now at the renewables and see if they actually, what they are and whether they will do the job. First of all, here's a solar farm. It's referred to as a solar farm because it takes up a lot of land. Nothing grows on a solar farm. The sunlight doesn't come through. It's absorbed in order to generate electricity. When these are built in the desert, and a number of them have been set up in Arizona, they have to move out the animals, the turtles and other creatures that are living in the desert, because they're in the way of the construction, but also they can't live under this. So this would convert a lot of green pastures and green prairies into, well, wasteland, just brown. And I want to show you how a wind turbine gets built. This is Mid-American Energy, which is one of the installers of wind energy. Take a look. You'll see it's a major construction project with significant environmental impact. It is not some small do-it-yourself project. I think you get the idea. This is a major construction project, heavy industry, not your small scale backyard project at all. So this is why this is an interesting graph from basically from the Department of Energy. What it does is compare the material requirements per unit of electricity generated for 5 sources of carbon-free electricity. And you can see that solar and wind, because they're so widely dispersed, they're relying on a relatively weak energy source, dispersed sunlight and wind, compared to concentrated energy that's in a nuclear reactor. They require vastly more materials of all kinds. And you can see cement, glass, the other, I'll show you the other in a second. There's substantial requirements here. I mean, one way I think about this is that on a small scale, solar is nice. You can put it on your roof and it doesn't have much impact. But if you're thinking about running this society on solar and wind, you're talking at a whole different scale of industry and material consumption. So here's some of the materials that are involved in solar, wind, and batteries. They're not, again, easy to use materials. They come from mining, extensive mining, particularly in China, Africa, other places. They have this, doing this on a large scale, on a much larger scale than we're now doing, will have even greater environmental impact than it has now. And they generate a huge amount of waste. I'll say a few things about nuclear waste in a little while, but here's an example of solar and wind waste. This is Puerto Rico after Hurricane Maria came through. The wind farm, the fans got broken by the hurricane winds, and the solar panels on the ground were smashed to pieces by the wind. And this is all toxic waste, because a lot of these materials, if you try to recycle them, involve rare earth metals and various things that are we tend to ship out to China and other places and let other people deal with the residue from our waste stream. And this is a huge waste stream, especially if you think about trying to run the country on it. So there are practical problems that I think explain why solar and wind, in spite of the support they've had, both financial and political, over the last 50 years, still are a very small part of our energy mix. It's hard to quantify, but the decision-making, the decision to install any of these, any place in the country, is broad, diffuse, involves many individual decision-makers in thousands of communities and millions of homeowners if we intend to go all the way to trying to basically power our country, our society here and globally with these sources. They have to agree that they want these facilities installed in their neighborhoods already. You've probably read or heard about people who don't want to see the windmills offshore from their summer retreats on Cape Cod and other places. I think it's, as I say at the end here, I think it's why solar and wind share output is still in the single digits. So there's another problem, very serious problem, which is they're intermittent sources. The sun doesn't shine at night and only shines part of the time in the daytime. In fact, the average is 18, with solar in Maryland gets about 18% of its maximum possible output if you install a solar panel in Maryland. But what people find, what Germany, which has been most active here, but also California, which has made the most progress in installing solar and wind, is that as you install more and more, it becomes worth less. Every additional megawatt you install is worth less than the previous one, mainly because what you're doing is adding more generating power at the time at which the sun is shining and the wind is blowing, and you don't need it then. You need it at other times. And so it becomes less and less valuable, and In fact, the German program has stalled because it doesn't pay to add more, and they start to run into opposition from people who don't want more windmills in their backyards. The best studies of this that I've found are done by a team at MIT. Jesse Jenkins was one of the leaders and has been giving a series of very, very interesting talks. I have a few slides here from him. He's now at Princeton and he's an assistant professor at Princeton, but worth following. What he's done is look at what happens as you increase the share of renewable energy in an energy economy. He looked at New England, and here's what he finds. As you start to increase the share, it gets more and more expensive because you have to build all this solar and wind that's excess beyond what you can actually use, and you start to curtail a lot. That's what the right scale. Curtailment is not using the power that is being generated because you already have enough when, as I said, when the wind is blowing and the sun is shining. So overall, I think my conclusion is solar and wind are first too weak individually, so you need massive amounts of them. They have to be too widespread, so there's thousands or millions of local decisions, and they're too unpredictable. So you need both to build excess amounts of them, and then you have to have backup for when they're not shining. You either need long-term storage, even from summer to winter, because there's much less sunlight in the winter than in the summer. But we don't have anything close to that, even conceptually, or burning it with backing up with natural gas, but then you're creating carbon dioxide. So they're just not suitable for the running the society. Some of the advocates blame the fossil fuel industry for the sluggish growth of solar and wind, but they're wrong. The fossil fuel industry loves renewables because they need backup, and they know that the backup will come from natural gas. And this is BP's advertising a year ago. We're a perfect partner to renewables, they say. And they, on the other hand, they hate nuclear. Here's an ad. Nuclear power, because natural gas prices have gotten so low, nuclear power stations have tended to need some subsidy today because their cost is greater than the low cost of natural gas. And this is an ad from, as you can see up there, the American Petroleum Institute opposing what they call nuclear bailouts. Other people call them clean energy subsidies or other names. But the fossil fuel industry, the petroleum industry, knows that the other source of backup to solar and wind, or to put it a different way, to baseload electricity, to produce baseload electricity, is nuclear power plants like Calvert Cliffs. So this is again from Jesse Jenkins. He produced this conceptualization of the kind of energy we need to address climate change. He talks about renewables as fuel saving. They don't need fuel. They just run on the energy coming from the sun. On his blue diagram, the blue portion of this is ways of adjusting demand, particularly if there's a high demand in the midday during the summer to reduce the load. But finally, there's what he calls firm low carbon sources. By firm, he means reliable, always available when you need them. And nuclear is the one there that's real and expandable. CCS is carbon capture and sequestration. As I say, it's in development, but it doesn't exist. Biomass and biogas actually are carbon neutral, not carbon free. And long duration storage doesn't exist. So nuclear is the one thing down there that's real. He's avoiding getting into the renewable versus nuclear controversy by using this framework, and it serves him well. Here's the result of one of his studies. If you omit the firm resources, the cost as you get down to zero CO2 emissions, the scale here is going from carbon emissions today to zero, say by 2050, the cost just skyrocket because of the intermittency of the renewable sources. If you build in some firm sources like nuclear, the costs are very, very much lower because you have a steady, reliable base load. And you don't have to overbuild the renewables so much. So let's talk about nuclear power. It has a long history in the United States going back to 1950. The first reactors built, well, there was a prototype in Shippingport, Pennsylvania, and there were the Hyman Rickover and the submarine-based reactors that he built, and that had a great influence on the design of power-producing reactors like the Shippingport one. We then had commercial reactors built in the 60s and 70s. Remember, Calvert Cliffs went online in 77. There's now underway what's called Generation 3 reactors. There's several being constructed in South Carolina and the United States, but a lot using the same models Westinghouse designs in China, South Korea, Taiwan, other places around the world. And then people are developing a Generation 4, which I'll talk about in a few minutes. So here's the story in the United States. These are reactors that are operating today across the country. Mostly you can see on the East Coast and around the Midwest, a few in California. The trend line here shows that you have to hunt for it a bit. Here's the nuclear line. It goes up and then it levels out. We've had no new nuclear plants built or gone online since the late 80s, basically because energy consumption in this country has been flat. And there hasn't been a market for the kind of large-scale investment that nuclear power requires. This shows the same thing. This is the growth of actual nuclear power. These were permits, but these were never built. Or at least the difference here is the ones that didn't get built because the market didn't exist for them. So we've been basically flat in our nuclear generation, but substantial. If you remember, it's about 20% of our electricity today comes from nuclear power. The key problem with nuclear power is that people are afraid of it. This is a typical survey. People love solar and wind, and they are not so favorable, or they're very unfavorable towards nuclear power. Well, this has a lot to do with the history of nuclear energy in the world and in this country. I put up this chart. I've been involved, as I said, in the 60s. I was involved in the U.S. Arms Control and Disarmament Agency in getting the test bed and getting the limits on missiles. I think when I spoke here in 65, I was talking about limitations on nuclear missile deployments. But people who organized in the 60s against nuclear fallout and in favor of banning atmospheric nuclear tests, when the treaty was signed in 63 and the Non-Proliferation Treaty in 68, they shifted their attention to nuclear power. They'd already become agitated about the radioactive fallout from nuclear testing, and they translated that into opposition to commercial nuclear power. And then there were the three, I'll say, notorious accidents. The 3 Mile Island in 79, which was just a couple of years after Calvert Cliffs was built or went online. And then there was the Chernobyl accident and the one in Fukushima. I'll have more to say about them in a few minutes. So there were really two nuclear myths. When I was in the government 60 years ago, we were told there was a missile gap, that the Russians were way ahead of us. It turned out when we actually sent the first photographic satellites over Russia, we discovered, in fact, they had 4 ICBMs, and we already had dozens and dozens, and soon the missile gap was in our favor. It was one of the myths. And the second myth is that today is that nuclear energy is too dangerous to use. the result at the moment is we have no good answer to climate change, and we continue to burn more and more fossil fuels. And I think we have to get smart and understand that there's huge misunderstandings about nuclear energy. Here's the results of 3 serious scientific studies of those 3 accidents. The 3 Mile Island, there were no deaths. No one died as a result of the meltdown. One of the reactors melted down. And the President's Commission, it was run by Dr. Kameny, who was the president of Dartmouth at the time. It said, in spite of serious damage to the plant, most of the radiation was contained. The actual release will have a negligible effect on the physical health of individuals. At Chernobyl, people did die. The first responders, mostly the firemen who came, there was basically the reactor overheated and caught fire. The carbon in it caught fire. The 28 people died as a result of radiation sickness from Chernobyl. The UN Scientific Commission that has been looking at atomic radiation for the last, almost 40 years, more than 40 years, concluded there's no persuasive evidence of any other health effect in the general population that can be attributed to radiation. And finally, at Fukushima, 3 reactors melted down because the tsunami swamped the backup generators that were supposed to keep the reactors cool. There were no deaths from the accident. Estimated 18,000 people died from drowning, and 1,000 died from as a result of being evacuated. But the evacuation was really unwarranted. The scientific commission said, in general, cancer rates are expected to remain stable for the population affected by the accident. A discernible difference from pre-existing levels due to radiation exposure is unlikely. That is, whatever effect the accident may have had is too small to measure. And here's why. This is the National Academy of Sciences has had a continuing committee going for now 40 years called the BEIR committee. It's biological effects of ionizing radiation is what that stands for. And this is from their most recent report, which is from 2007. And basically, it tells us that 82% of the radiation we're exposed to is natural background radiation. Comes from the rocks, comes from the food we eat, it's in our bodies, it comes from cosmic rays from outer space. Every time we eat a banana, we get a little bit of potassium-40, which is radioactive. About 16% is man-made. Of that, 1% can be attributed to nuclear power, to radiation from nuclear power plants, including the consequences of the 3 accidents. There have only been 3 major accidents like that. But most of the radiation we're exposed to, we choose medical x-rays and nuclear medicine, radiation treatments, and then just consumer products we buy have or just everything is radioactive. Human life and all life grew up in a radioactive environment, and we live and survive within it. And here's the nuclear waste issue. If you ask people, what about nuclear power? It's one of the first things they will say is, well, what about the waste? Well, here's the waste. This is what it looks like. This is waste from a reactor, spent fuel it's called, and they're put in these what are called dry casks, and they're perfectly safe. They don't hurt anybody. The hot radioactivity is already decayed. What people don't understand is the long life radioactive is weak. That's why it's long lived. And it's just very weak. And it's really very small compared to the waste I showed you before from solar and wind. All the waste ever produced in the United States from nuclear reactors in the last 50 or 60 years would fit in that football field. If you stack it about 40 to 50 feet high. And it doesn't pose a danger to anybody. It just sits there. In fact, there's a way to actually use it up that I'll come to in a few minutes. So here's another part of this history of reactors. So I call your attention to the chart. The blue is the cost of reactors built in the United States. And you can see what happened is after the 3 Mile Island accident and after the fears of radiation generated by people who were, as I said, anti-nuclear activists, nuclear power started to get more expensive because they started to have to add all kinds of new measures to protect the public from the radiation that they were afraid of from these reactors. You can see the cost going up. Brett Kugelmass talked to you back in February about this and about how his view was the nuclear power industry became a nuclear safety industry instead of a power industry. Other countries haven't gone quite in that direction, and this is said today. Here's China. This is a AP1000. It's a Westinghouse design, and it's being built at $3,500 per kilowatt. You can see the scale here. The reactors started like Calvert Cliffs at about $1,000 per kilowatt, but then it skyrocketed as we started to have to add additional shielding and very heavy containment vessels and so on. Other countries are moving ahead. The United States, there's one nuclear power plant being constructed in South Carolina, and so far it's costing, I don't know, somewhere between $6,000 and $10,000 per kilowatt. Got a false start. They built it without having any blueprints, and they had to tear down a huge. Anyway, we haven't built enough to have any experience in how to do it anymore. Well, here's the model. This is generation 4 reactor. The newest models are small, self-contained, and self-protecting. That is, they're what's called passively safe. If they overheat, basically they expand. There are 2 models. Either they expand and the chain reaction stops automatically, or if they get overheated, a seal opens and they get flooded with water or with liquid sodium in some cases, and they turn themselves off. That is, there's no operator intervention needed. This is a model. This is a model of what it would look like to transport a nuclear reactor and to take it out to its site and install it. The costs are estimated between $1,000 and $2,000 per kilowatt. What you need is either a market where you expect electricity to need demand to grow, or you need government policy, which will require that existing fossil fuel plants be replaced by nuclear power plants. These generation 4 reactors, they can't melt down. Some of them are breeder reactors. That means you can take the existing waste, which is mostly just uranium-238, and consume it as fuel. Basically, you put it in the reactor, it gets converted to plutonium. The plutonium breaks apart in fission, produces energy. You end up consuming most of the waste. The radioactive waste that results is much smaller, and it'll last perhaps for a couple of hundred years of radioactivity, not the thousands that we have now. The fuel would be reprocessed internally, so you wouldn't have the worry that, again, is expressed that people will use reactors to generate bombs. These can be built in factories rather than on site, so you just build it at the factory like you build an airplane in a factory, and you carry it to the site and put it in a hole in the ground. And there are being dozens of these models are being developed around the world. So my conclusion is, in short, is that solar and wind are simply too weak, too widely dispersed, too variable to power a modern society. Nuclear power is the only energy source that can expand enough and is reliable enough. The new types of reactors will be safe. They'll leave minor amounts of waste, and they'll cost about 1/3 of what renewables will cost. And finally, but very importantly, the public's unwarranted fear of nuclear energy has to be overcome because of this history of concern about it. I think younger people may not have as much concern, but it's still serious political issue. I offer you a quote that somebody sent me from John Adams, that facts are stubborn things, whatever may be our wishes, inclinations, or the dictates of our passions. They cannot alter the state of facts and evidence. And I suggest, if you want some facts, here's 2 books. This is a free book written by 2 engineers in California. It's a critique, takes apart the Mark Jacobson model of 100% renewables. It's Jacobson calls it a roadmap to 100% renewable. They call theirs the roadmap to nowhere. You can get it at you can download it from roadmaptonowhere.com. And then there's a very nice book written by a former professor of political science at American University, Joshua Goldstein, and a physicist from Sweden, Stefan Kvist, on how France and Sweden have converted their electric systems to all nuclear and reduced drastically their carbon footprint. So I suggest you take a look at those if you're interested further, and I'm happy to take questions.
Okay, thank you, Len. That was really interesting. I see we have a number of questions. The first one, and several people upvoted it, is there video of a nuclear power plant being built for comparison with a wind farm? Or let me rephrase it and say, can you contrast the construction methods for both types of installations?
Well, the difference is that you have to build those wind turbines everywhere. If maybe you saw in the video in the background, you could see some more of them that they had built previously. They're widespread. Sure, the construction of a nuclear power plant, at least the kind we have right now, is a major construction site, but it's only one site. You could see how big the site of Calvert Cliffs is. It's a few acres. No comparison. I mean, it's hundreds of acres to 1 ratio between the land that's required by a wind farm and the land required by a nuclear reactor.
Okay, thank you. Next question is, someone would like to know more about the toxic waste streams from solar and wind. Of course, the actual generation is generally waste-free. Are you talking about the manufacturing or about the disposal of waste or the exhausted panels, whatever?
Well, you have to, the photovoltaic panels involve a variety of materials, lithium, sodium, and a number of rare elements, rare metals. And the wind turbines involve various kinds of ceramics. There are already dump yards where there are hundreds of the waste fans that just there's nothing you can do with them. They're these very high, very specialized ceramic, lightweight, relatively, but of course many tons, as you saw in the video, of waste. When you have to recycle them, I mean, there's another issue about lifespan. Nuclear reactors, there are reactors now that have been licensed for 80 years. Wind farms, a particular wind turbine will last somewhere ideally between 20 and 30 years and then have to be disposed of. And a PV panel will last maybe 20 years before it deteriorates from just heat and sun and needs to be replaced. So you have a continuing turnover of these materials, which produced a waste stream that is toxic because of all the materials that are used to make these. The wind turbines also, the electrical turbines inside also require a number of exotic materials. I'm not an expert on that, but I know that you don't want a dump yard for wind turbines or solar panels in your backyard. Let me just put it that way.
Okay, thank you. Len, the next question is, it's not really a question, but it's a comment. What are your thoughts on thorium reactors, and are they a viable alternative to for nuclear power without the stigma of uranium?
Well, they don't have the stigma of uranium, but they have the stigma of fission, and they produce waste. If they're a breeder, some of the models of thorium reactors will produce very little waste, because the breeder reactors will basically consume their own waste. And it's sure, it's a viable alternative. There are a number of these. It's part of the Generation 4 mix that people are pushing. A number of them are now up for Nuclear Regulatory Commission approval and licensing, so they can start to find customers who will, utilities that will install them. The Canadians are going to go ahead and install, I don't think it's a thorium reactor, I think it's a uranium-based reactor. But again, I really don't think it's the stigma is with uranium, but the stigma is with nuclear, the word nuclear. And certainly a thorium reactor, the way it works is it converts the thorium to uranium and then uranium fission. So you can't get away from it that easily, I'm afraid.
All right, thank you. A comment on the Chernobyl incident or accident. The comment is that saying there have been no other health effects beyond the 28 first responders who died strains credibility. Can you comment further on that?
Yeah, it's not that there are no other health effects, it's that you can't identify them from the general background. People estimate that there were probably, iodine is the shortest lived and therefore hottest radioactive element, particularly one that has biological impact, that is, it's absorbed into the thyroid of particularly of young children through milk and meat and so on. And there's an estimate there probably were 4,000 cases of thyroid cancer, childhood thyroid cancer, as a consequence of the Chernobyl accident, and probably about 60 deaths from because childhood thyroid cancer is treatable. So they estimate that of the 4,000, probably about 60 have died. That's the numbers I've seen. But you can't identify them because of the large background of other sources of radioactivity that produce the same ailments and the same ratio, the same number of deaths, in fact, much larger. The problem, if you like, is that the radioactivity, even from an explosion, which the Chernobyl reactor, which is nobody would ever build in the West would ever have built such a reactor, I should say. Certainly not for power, not for commercial power. Anyway, the problem is that the radioactivity produces is so small compared to the radioactivity that exists already in the general background. And what the scientific commission is saying is it can't distinguish it. The contribution from that accident is too small compared to the general background to be able to identify its consequences as compared with just the general background that we experience. Certainly in the short term, you could see short-term, short-lived isotopes that would only come from a reactor, but now we're talking 30, 40 years later. And although that report was a fairly recent one, but if you go back, you can't see any consequences, and because of the relatively small amount of radioactivity that comes from even these kinds of accidents, particularly meltdown. Think about what a meltdown is. I mean, I think maybe you remember Kugelmass talked about it a bit. A meltdown, it melts down. It goes down into a hole in the ground and becomes a solid mess. It costs a lot for the company or the country that has to seal it over and lose the energy resource. But it doesn't have any external impact. It certainly is not going to China, as the China Syndrome movie suggested. It's just going to sit there in a solid metal puddle, not liquid anymore, of course. But it's not going to go out into the atmosphere. It's just going to be entombed forever.
Okay, moving on to the next question. I'm paraphrasing here, but it basically says we've lost expertise in the industry and no longer really know how to build large nuclear plants. The net result, and with the cost overruns, it's basically the same cost to build wind or solar plants for the same amount of power. So would you like to comment on that?
Yeah, no, that you see the the comparisons. I think what you're talking about is these comparisons of what's called levelized cost of energy, and it's true that if you look at those comparisons, nuclear power is comparable with the levelized cost of solar and wind. The problem is nuclear power will run 24 hours a day, 7 days a week, 365 days a year. Wind and solar won't. They need to be overbuilt in order to get the total power that you need, or they need a backup in the form of either battery storage or natural gas, and you have to include those costs. And the reason I showed you the Jenkins analyses is that if you look at a system and look at what the system costs are with renewables as opposed to renewables plus a steady nuclear firm source, the renewable source is much more expensive because it's intermittent, because it has to either be overbuilt or have a supplemental backup, and either of those adds substantially to the cost. That doesn't even include the additional cost of transmission, because you need transmission lines, going from every wind farm and every solar farm into the main lines, and those costs usually aren't included. They're not as huge as the installation costs, but they're substantial, and there's a lot of community resistance to installing those extra power lines. So you're going to run into the same problems you have now in trying to site these facilities. In New York, the governor has put through legislation that allows him to override community-controlled neighborhood, local, county, and city control of the siting of these facilities. So there's also seems to be a contradiction between democracy and renewables. You can have one or the other, but may not be able to have both.
Okay, thank you. Next question is, do you think the ideal solution is mostly nuclear with some residential solar and wind to supplement? Is that your suggestion?
Well, solar and wind don't hurt, but they do create some costs and some strain on the grid, because the grid has to figure out how to accommodate a substantial amount of solar and wind, which don't come in response to demand. They come in response to the weather. They're what the grid people call non-dispatchable. I mean, quite frankly, I don't see a need for the renewables. If you have a system composed of nuclear plus some storage capacity, you can overbuild the nuclear and then store the extra because nuclear doesn't ramp up and down very quickly in response to changing demand. But if you overbuild it and have some storage, the storage can respond to the short-term fluctuations in demand. People also suggested that you could use nuclear if you make it cheap enough. You can use it to extract carbon from the sea and produce hydrocarbons, produce liquid fuel, gasoline, in effect, carbon neutral gasoline. So instead of having to electrify everything, you can in fact run the existing auto fleet, for instance, and the airplanes with a carbon neutral fuel if you have a cheap source. And it looks to me and to other people that these small modular reactors built on a large scale, not the big reactors we're building now, but these small modular reactors built in factories and just turned out, you talk about turn them out the way we turn out jet aircraft. They're a comparable complexity. Could produce fuels that would be carbon neutral and would address the major problems we have in powering transportation and trying to make a conversion to on an all-electric, trying to think about it. An electric 18-wheeler is a little hard to imagine. The batteries would be half the weight of the truck.
Okay, next question, Len. What drove you to change your mind about nuclear energy?
People pointed, I actually, what woke me up was a talk by a man named Michael Schellenberger. You look him up at COP23, which was one of the annual conferences dealing with climate change. It was about 4 years ago in Berlin or in Bonn. And he gave a talk on, which featured Germany's attempt to go renewable. And he made just basically the points I'm making, that renewables are too intermittent, too expensive, too unreliable, and too environmentally destructive in terms of both the space they take when they're running and the materials that they require if you're trying to go large scale with them. And then he compared it with nuclear and pointed out that the nuclear fear that nuclear is carbon free, that the extra cost is clearly a result of the fears that people have developed around nuclear. And if we develop and install nuclear plants that are safer and that people feel more comfortable with, every city can have its own nuclear reactor. It can be a showcase in the downtown area. I found it persuasive, and I then looked into it further, and the result is what the talk I've just given you.
All right, thank you. The next question is, if nuclear power totally penetrates the market, what's the steady state amount of waste that we can expect to generate?
Waste. Well, first of all, if we install the breeder reactors, the GE and Hitachi, for instance, have a model that actually we had running in the United States out in Idaho at the Idaho National Laboratory until it was actually, believe it or not, shut down by Clinton and Gore in 1994. It's a breeder reactor, and it can use the existing fuel that we already have for the next 100 years. You wouldn't have to mine any more uranium. You could just take the existing fuel, which is, as I said, mostly uranium-238, and use it as fuel in a breeder. You'd breed plutonium and fission the plutonium and reprocess it internally. Basically, you have the next few hundred years with existing sources of uranium. The amount of uranium actually is almost endless because there's a lot of uranium dissolved in the ocean. You can pull it out of the ocean if you have to. The uranium path, until we solve the fusion problem and can get clean hydrogen-based fusion reactors, which is a dream, and I don't know if I'll ever get it. It's a source that's workable, it's stable, it's safe, and it's basically supply of fuel is endless.
Okay. I think you may have answered this question, Len. What's the environmental impact of mining the uranium that we would need for a fully nuclear base?
Yeah, we don't have to mine. We have so much uranium and plutonium stored away already from nuclear weapons that have been dismantled. We bought uranium from the Russians that when they were dismantling their nuclear arsenal in accordance with the treaties we have with them. And so we've got plenty of nuclear fuel for the next, at least for the next century, without any expansion of mining. I know people are concerned about the environmental impact and the human impact on the miners of uranium mining, but we don't really have to mine anymore in order to get the uranium fuel we will need, the fissionable fuel that we'll need for the reactors of the future.
Okay, thanks. Next question. Do we have U.S. companies that can build fourth generation reactors?
There are quite a number. The most famous, I guess, because of its chief sponsor is called Teraherth. Terra Earth. I think that's what it's called. Anyway, Bill Gates is the lead investor in it. And there are a number of companies, I think somewhere between a dozen and 24 companies in the United States that have models. GE and, combined with Hitachi have several models. They just announced one yesterday, a light water, a water-based modular reactor. They already have a sodium-based breeder reactor that they're trying to market also. So there are quite a number of companies, and they're starting to invest. It's expensive. The company that is the first in line to get a modular reactor licensed by the NRC spent $500 million on their application. So this is not something to be done lightly or very inexpensively.
Okay. Next question. I'm not sure I understand it, but perhaps you do. What are your thoughts on carbon dioxide electroreduction and the commercial viability of that process?
Well, let me duck it in a way. We need to pull carbon dioxide out of the atmosphere because we already have too much there, and it's creating continual warming. We've exceeded the 350 parts per million. We're up to about, I don't know, close to 420 now, and we need to pull it out. The question is, what do you do with the carbon dioxide? And it's a real problem. People talk about, well, bury it, but there are only a limited number of places where you can bury it safely and for a long period. So people have talked about ways to use it. And one way is the way I talked before, pull the carbon dioxide out, convert it into a hydrocarbon, and then burn it. But that requires a cheap source of energy, and that requires inexpensive nuclear reactors. I think that would be my way of dealing with it. But it is, what you do, the sequestration part of CCS is as much a problem as the carbon capture because of this issue I just mentioned.
Okay, I think you've answered this question. Seeing you're familiar with Brett Kugelmass, do you agree with him that we only need nuclear power? His comment to the questioner was, it's unnecessary, nuclear is sufficient. Renewables are unnecessary.
I agree with that. I mean, some people I'm working with on this issue want to keep renewables, but I think it's mostly because they're so popular, and you don't want to turn people off who are climate advocates, advocates for doing something about climate change and believe in renewables, but they really aren't needed because they're not dispatchable. They don't respond to demand, and they don't meet a need. I mean, the one place where they might meet a need is, in rural areas and isolated areas where, I mean, people even talk about micro reactors, having 4 megawatt reactors out for very tiny towns and so on. But I can see in isolated areas, or if you have a farm or someplace, you certainly, solar and wind would be fine, but you still want to be tied to the grid because you're, in the middle of the winter when the sun isn't shining and the wind is blowing, you still like to have the lights on.
Yeah. Next question. What are your comments about space solar as a renewable type source of energy? I take it that means generating electricity or generating power in space and then transmitting it to Earth.
I don't see that it's economically any improvement over generating it on the ground. You guys know better than I how expensive it is to put stuff up there, and I'm not sure the gain from having it up a few hundred, I don't know, a few miles or a few hundred miles would be worth the price. Especially when you have nuclear power. I mean, I think we're fortunate that we discovered nuclear fission, and that you can run an industrial modern society on nuclear fission, and it's the only way. To me, as far as I can see, it's the only way to actually do it. But we can do it, I mean, things just will, if we get sensible, really will work out in the right way. But if we keep heading on the renewable path, in New York State, the governor is still heading off in renewable. We just shut down this reactor just north of New York City. It's a tragedy. It was working perfectly well and would keep working for another 50 years, as far as we could tell. But the neighbors were afraid of radiation. And
Okay. Next question. Can you comment on uranium coming from politically unstable countries elsewhere in the world, which is one of the problems we have with petroleum?
Well, the problem is far worse with the materials that solar and wind would require, because, you know, the third world is where you can get these rare earth materials, and the lithium comes from Latin America and so on. But again, we don't need to mine uranium right now. We can use reactors that use the existing stockpiles of uranium that we assembled during the arms race, and now have sitting in warehouses waiting to be used. And we can use them and reuse them. As I say, the waste, about somewhere between 98 and 99% of the uranium that was in the fuel that fueled the existing reactors is still there and can still be used. People refer to it as fertile. That is, you can irradiate it and produce a fissile material, namely plutonium. You add 2 neutrons, capture 2 neutrons, convert it to plutonium, and then burn it. And you can go for a very long time with the existing stockpiles of uranium and plutonium without having to open up mines that will be destructive of the environment and the livelihoods of countries around the world.
Okay. I think we'll answer or ask one more question and then we'll close things. Can you comment about the cost of managing nuclear waste until it is acceptable or safe? Presumably a long time.
Well, yeah, it's not very, what does the waste look like at the reactor? I've seen the waste at the reactor at Indian Point, which is the plant up in Westchester County, north of New York City. And it's basically a bunch of large casks, like you saw in that picture, surrounded by a fence. You may want to have a lifeguard operating around the fence, or you may just want to electrify the fence and not have anybody particularly guarding it. There's no particular manpower. I mean, the Finns decided they're agreeable to burying it. Somehow or other, the people in Nevada didn't want it to be buried there, but it could be buried in Yucca Mountain in Nevada, and pay the people of Nevada to keep it there. It wouldn't hurt them or anybody else, and it would just sit there. Of course, you want it so it's open so you can take it out and use it in these breeder reactors that hopefully we will have, and that will last humankind for the next couple of 100 years until we may need to assemble more fuel, or maybe we'll have fusion by then.
Okay. Actually, one more question for you. Are there any signs that the current status quo on nuclear is changing?
Oh, yeah. The federal government is sponsoring demonstration, put out demonstration funds so that the new Generation 4 reactors can be demonstrated at the National Lab in Idaho. And I say there are these startup companies that have models ready to go if they can get the NRC to license them. The presumptive presidential candidate for the Democratic Party is supportive of nuclear energy as well as other forms. He doesn't want to turn off the supporters of renewables. Even the presumptive Republican candidate supports all forms of energy, including nuclear, and the Department of Energy is supporting, as I said, the development of nuclear power. What it's not doing is setting the framework that will basically require that electric utilities convert from fossil fuels to nuclear. And that's what we need. We need public policy that says we have to convert to a carbon-free source. And basically, I'm saying, and I agree completely with Kugelmass, that it can be done. He thinks that he's got to go to some country else other than the United States, that we're hopeless, but I don't believe that. I think we're a pretty smart country if we put our minds to it.
Okay, great. I'm going to call it to an end there. Thank you, Len. If we had the audience audio, I'm sure you'd be getting a well-deserved, ovation from them.
Thank you. It's been a pleasure.
All right. And let me just apologize. We have many more questions, and I'm sorry if your question didn't get asked or if I mangled it in translation. So thank you, everyone, for attending, and hopefully we'll have another virtual colloquium soon. And again, thank you, Len, for a great talk.
Pleasure. Thank you.